All right, welcome back to the final section of this unit. We are in one of my favorites. We are in the application portion of our quadratic unit. And this is very good because this actually lets us discuss where this math applies, right? Application. So what we're going to do is we're going to analyze some real world scenarios. And then we're going to model them using quadratics. And then we're going to answer these problems within context. Remember, we got to talk about what is making sense and why we are talking about it and all of that good stuff. So always make sure you answer these problems within context. All right, so there's a couple things that I want to talk about first before we jump into it. Number one, if you are using a TI-84, I'm going to show you a couple things on here. We have done this before in our last unit, but these are just some little quick calculator tips if you're working on the TI-84. Remember, you can always do stuff on the computer on Desmos, but it is good to learn how to do them on the TI-84. If you're working on an Inspire, hit up YouTube and figure out how to do it on YouTube. I'm not that proficient with the Inspires, so this is my jam right here, TI-84. So this is just talking about how to get that quadratic graph in there and find those parts. The part that might be a little bit new for us that we haven't really done is this section right here. Okay, we have this window function, and this just kind of, broadens up our view to fit what we need to fit into the graph, because that little calculator window isn't always the biggest. So you might want to pay attention on this part right here. All right, I think there's another part. Yes. Things to know. So I put some key points right here, just some stuff to consider when you are looking at these applications, because we really want to understand what it is that we're talking about. And this is kind of a recall on some of our previous information that we've learned. Remember, anytime we have two variables, we're really looking at our independent and our dependent variable. Remember, that is our x-axis and our y-axis. We got these two different quantities that we're talking about in relation to one another. Okay, and one of the most common examples that we use in math, just because they work really well and they describe a lot of the stuff that naturally occur in the real world, is time and height. Okay, this is just a good one to start with. One, because time is really easy for us to understand that it is independent, because time cannot, be dependent on something. Time just continues to go whether we like it or not. And then when we talk about height in relation to time, if something is moving, this could be height or distance, right? Whatever you want. This is related to time. And remember, we have a graph like this, and what this means is all of these points on this graph are in x comma y. Okay, there is some point. Okay, so like here at our vertex, this is telling us, hey, at some certain amount of time we had some certain amount of height. Okay, our intercept, right? Okay, at some certain amount of time there is no height, right? Remember, an x-intercept is when we have a y value of 0. Okay, so if we have a value of 0 for height, that means it's like on the ground, right? Okay, and then there's this important intercept over here. Okay, and the reason that I want to talk about this a little bit is because sometimes we have to think about the solutions within the context of the problem. Can this be a solution? Would this make sense? Okay, if we had this intercept over here, well, we know at the origin, which is what, 0 comma 0, then this would have to be a negative number. Could we ever have negative time? No, we could not. So in this unit, or in this section rather, you're going to see where we might have two answers, and it's really up to you to pick the one that makes sense, because one of them might not make sense. Okay, so remember, we're identifying those key elements, the intercepts, the vertex. Those are good parts for us to recognize. And then last but not least, if you don't have a graph present, anytime we're doing any kind of word problem, draw a sketch, kind of try and figure out what it might look like. Do a rough sketch, doesn't have to be perfect, but just kind of play around with it. So that's just a little bit that I wanted to talk about before we jump into it. All right, so we got our first example here, example number 1. So first things first, we always read. So let's check it out. A ball is thrown straight up from a rooftop, 560 feet high. The formula below describes the ball's height above the ground. H in feet, T seconds after it was thrown. So we got our two variables. H is our height in feet, and then T is our time in seconds. Okay, so very important to remember that. The ball misses the rooftop on its way down. The graph of the formula is shown. Determine when the ball's height will be 490 feet and identify the solution as a point on the graph. So we got our function right here. Okay, so it wants to know, determine when the ball's height will be 490. When the height will be 490. Well, what do we know about this problem? Okay, we know that we are looking for time, right? Because it's giving us 490 feet. Determine when. Okay, if we're asking when, that means we're looking for time. So if we got a function with h and t, looks like we are trying to solve for, you guessed it, the t. So let's go ahead and plug that in. We got 490. We can plug that in for our height. We are wondering when, using this formula, it will equal 490 feet. So we do that as such. So we got 490 is equal to negative 16t squared plus 102t plus 560. Okay, now it looks like we got a quadratic that is not in standard form. And remember, this was back in our factoring unit, right? We said always put it in standard form. So let's go ahead and get rid of this 490. We're going to subtract that from both sides. So we're going to get 0 is equal to negative 16t squared plus 102t, and then 560 minus 490. That's going to give me positive 70. Okay, so now we got this quadratic. We got this negative term out front. Okay, remember in our factoring we don't want a negative term, so let's go ahead and factor out that negative. We can do that by multiplying both sides by -1, right? Remember, we've done stuff like this before. So that's going to give us 0 equals 16t squared minus 102t, and then we got minus 70. Okay, and then if you remember our factoring unit, first things first, after we're in standard form, we always ask ourselves, is there a GCF that we can take out? Okay, so we would want to try and divide everything. Okay, let's try dividing everything by 16. Well, can 102 be divided by 16? No, it cannot. Well, what would be our next factor from 16? Maybe 8? Can we do 102 divided by 8? Does not work either. What about 4, right? 102 divided by 4? That doesn't work either, so it looks like it's going to be 2, right? Oops. Divided by 2. All right, so 2 is the greatest common factor that we can take out. So let's take out that 2. So this is going to give us 8t squared, okay, minus 51t, and then we got minus 35. All right, now this looks like some big numbers. Okay, so we can factor this. I'm going to let you pause the video. You do the factoring because we've factored before. Unpause the video, come on back, and you're going to see what I got. All right, welcome back. So I went ahead and factored that, and I got 8t plus 5 times t minus 7. Remember, that 2 is just sitting there on the outside. We don't really have to worry about that. So now we want to use our zero product rule. Remember, we are trying to find the value of our zeros. Our zeros are our x-intercepts. Okay, so let's go ahead and figure this out. So this first one, this is going to be t is equal to negative 5 over 8. And then this one is going to be t is equal to 7. So now this is where that part that I talked about where we want to figure out within context of the problem, is this a solution? Okay, remember t is describing time, right? Okay, so if this first solution here is -5/8 seconds, can we have a -5/8 seconds? No, we cannot. So this definitely cannot be a solution. So that means this one right here is going to be our solution. So let's go ahead and check this, because they actually did give us the graph in this problem. This is saying that the ball will be 490 feet at 7 seconds. So let's go ahead and look at 490. I'm going to draw a line right here. So this is going from 0 to 140, but it has a halfway marker. So that's probably going to be 70. 140 plus 70 will be 210, right? So it looks like these are going by 70. So 420 plus 70, this is going to be that 490. So at 490, we stretch all the way to the end of the graph right here. And then if we followed this down to find our x value, oh, would you look at that? 7 seconds. So yes, this is telling us that at 7 seconds, we are at 490 feet. Okay, so that is how this works. All right, so conversely, I want to show you guys this. All right, so I got my calculator up here. So what we could do is we could enter this function. Let's go ahead and do that. Y equals, okay, if you got to clear something out, clear it out. So let's do that, -16. We can use any variable. Our calculator uses x. That's going to be the same thing as t. We just know that it means t in this case. We're going to square that. Plus 102x, and then we got the plus 560, right? Okay, so if we go ahead and hit graph this, we might not see the graph because of what our window looks like. Oh, we got a little bit of it, and then boom. All right, that doesn't even look like a parabola. So we got a couple of different options. One, we can use this zoom button. Okay, and then you got these different types of options right here. Okay, so we can zoom out. You got to hit that like a couple times. And I recommend playing around with your calculator, get to figure it out a little bit. But we have this option 0 called zoom fit. And sometimes that helps us and sometimes it doesn't. Let's go ahead and take a look at what that does for our graph. This is telling us to fit the graph in the window. Okay. So this one looks like it can help us a little bit. Okay, this is kind of cut off way at the end. It might be hard to do the intercept function right there. Okay, so this is where that window comes in. Okay, so we have this window button. Okay, and then if you can see the window that we're in right now, it gives you these little options right here. So our x minimum, remember that is how far left our x-axis is going. Our x-max is how far our x-axis is going to the right. And then how we're counting our scale by. Okay, and then we have our y-minimum, which is the lowest y value. And then our y-maximum value. And then how we're counting our scale by. So let's go ahead and play around with this for a little bit. If we look at our x-axis, we know we're going from 0 to 12. So let's go ahead and do that. We're going to do our minimum is going to be 0, and then it looks like we're going to 12. Okay, and then how is this scale being counted? Well, they're counting by ones, so let's go ahead and do by ones. Okay, our y minimum is also 0. Okay, and then our maximum, well, it looks like they had 770. Let's try that. And then our scale looks like they're counting by 70s. So let's try that. Now let's hit graph and see what it looks like. Oh, what, Mr. Martin? It looks exactly like it does on my paper, man. That's crazy. Okay, so we got this graph right here, which is this function right here. But we wanted to know what 490 is. And if we plug that 490 in for h, remember this is like function notation. Instead of saying y equals, this one said h equals. But let's treat that like it's the y, because that's basically what it is. And we said this h was 490, so if h equals 490 and h equals y, here let's go ahead and do that. H equals 490 and h equals y, then y equals 490. All right, let's try that. 490. We're going to draw a second line in here. And now let's graph it. Let's see what happens. Oh, what? Man, Mr. Martin, it looks like you know what you are doing. So remember, this was that point where we found 7 and 490. So we can use a calc function to find this actual value right here. So let's go ahead and do that. We're going to do second and then hit that trace button. We don't want the value. We don't want the zeros, minimum or max. We are looking for where those two lines cross each other. So that is the intersection. Okay. So the way that this works, remember, this is a little bit different. This isn't left bound, right bound. This is called first curve, second curve. Right now we're on one line. You can do it wherever you want. You can be way up here if you like. You're going to hit enter. You're going to see it snap to the other line. It's going to say second curve. You can just hit enter again. And then as always, it asks you to guess. We hit enter a third time. Bam, it snaps to that intersection point. And would you take a look at that? 7, 490. We are good to go. Okay, so that's how you do it on the graphing calculator. And then as usual, remember I said you could do it on Desmos. So we said we were looking for y equals 490. And then what was our function? Negative 16x squared. Here, let me pull it back up. Plus 102x. Plus 102x, and then we had plus 560. Okay, so we could do the same thing. Let's go find, boom, it's going to be like way up here because Desmos is like that. So we are looking for that line at 490. We're looking for this point right there, 7, 490. So these two little utilities are going to be very helpful for you to use for this section. Okay, all right, so enough of that. Let me bring this down and pop this back up. We're going to go to the next example. All right, example number 2. It says a rectangular parking lot has a length that is 7 yards greater than the width, the area of the parking lot. And yeah, I said park in. There's no G on there. This is the park in lot. It's 540 square yards. Find the length and width. So when in doubt, draw that rectangle. Okay, remember, it's always helpful to draw it out and kind of get an idea of what you're doing. So we know it says the length is greater than the width. So right now the length is modeled after the width. So I'm going to call my width is going to be x. All right, and then my length is 7 yards greater. So that's going to be the width plus 7 yards greater. So my length is x plus 7. And then it gives me the area. So I know area is that big A right there. And this is 540 square yards. So I know what the area is. And then what's the formula for area? Area is equal to length times width. Bam. So now we got all our information. Let's go ahead and plug this in. So we got our width, length times width, or width times length. I like to just put my single variable on the outside. So we know that we got that area 540. This is equal to x times x plus 7. Oh snap, we got parentheses. That means we got to distribute. Let's go ahead and do that. 540 is equal to x squared plus 7x. Oh, we got a quadratic. What do we want to do with quadratics? We want to try and factor those. We got to get that into standard form. Let's move that 540. So we got 0 equals x squared plus 7x minus 540. Okay, can we factor that? We sure can. Go ahead, pause the video. You do the factoring because I've taught you factoring already. Come on back and see what I... All right, I know you got it because I taught you well. So we got x plus 27 times x minus 20. Let's do our zero product rule and find these solutions. X is equal to negative 27 here. And then we got this one, x is equal to positive 20. So can we have a negative length or width? Don't think so. So this is not going to be a solution. This is going to be our one that is a possible solution. It's realistic. It makes sense. So if we know that x is equal to 20, which one of these is just x? Boom, that is my width. So my width is equal to 20 yards squared. And then 20 plus 7, that's going to give me 27. Boom, look at that, so easy. As long as you know what you are doing. All right. Okay, so this one is not so bad either. All right, let's go to example number 3. Oh man, look at this. The image is already there for us. So it says a pool measuring 22 meters by 30 meters is surrounded by a path. So we got the pool right here. This is the path that is surrounding it. And it is a path of uniform width, meaning the same on all sides. X distance, X distance, X, X. As shown in the figure. We've actually done something very, very similar to this, so hopefully you remembered it. It gives us the area of the pool and the path combined. We want to find the width of the path. Okay? So let's do first things first. So if we know that this is 30, but we're trying to find with the width of the path on both sides, that would be 30 plus x. Plus x. So x plus x is 2x. Boom, look, they already gave it to us. They gave us this and they gave us this. So if we want to find that area, we need to multiply this and this. Remember, length times width. So let's go ahead and do that. Let's model that. So we got 30 plus 2x times 22 plus 2x. And it says the area of the pool and the combined path is 2,100 square meters. So we know we're setting that equal to 2,100. All right, let's go ahead and do our double distribute. Boom and boom. All right, so this is going to give me 4x squared plus 104x plus 660. Okay, so this right now is not modeled in standard form, right? The x is after the constant. I already went ahead and crunched this out. Multiply it how you need to multiply it, then put it into standard form right here. This is what you should get. Okay, and then this is equal to 2,100. All right, we got stuff on both sides. Remember, in our factoring, we wanted everything in one side. We want to see if we can factor this first. So let's go ahead and subtract that 2,100. That is going to give us 4x squared plus 104x. 660 minus 2,100, negative 1440. Boom. Is equal to 0. All right, we want to see, can we take something out? Yes, we can. We can take out that 4. So that's going to give me x squared plus 26x minus 360 is equal to 0. All right, go ahead and pause the video. Try and factor that out. If we can't factor it out, then we're going to use a calculator. But I'm betting you can factor it. So pause the video here, factor it, then come on back. All right, boom, great work. So I went ahead and factored it out. I even took it a step further and did that zero product rule to find my solution. So x minus 10, we would get a positive 10, which makes sense. That can actually be a solution because we can have a width of 10 square meters. We can't have a width of negative 36 square meters. So my answer is going to be 10 square meters. Remember, we are trying to find an answer within context of the problem. It has to make sense. It has to be a viable solution. All right, last but not least, we got example number 4. Let's hop to it. This is saying a football is kicked straight up from a height of 3 feet with an initial speed of 54 feet per second. This is our formula, negative 16t squared plus 54t plus 3. This is describing the ball's height above the ground. So height is our h, and then t is in seconds after it was kicked. How long will it take for the football to hit the ground? And we want to round to the nearest tenth of a second. So there's a couple things you got to think about. Look, we got no graph, so we can't just sit there and eyeball it. We got to do a little bit of math here. So always look at your function, okay? Remember, in our previous unit where we talked about the parts of a quadratic, and the beauty of standard form is it really shows us one thing. It just, bam, smacks you in the face, okay? And that is our y-intercept. So understanding where our y-intercept comes helps us create a generic graph to kind of help guide us. So let's just make a little rough sketch, right? Okay. We know that our x-axis, right, is time. So I'm going to go ahead and label this time. And the other one was what? Height. Our y-axis is height. So I'm going to label that height. Okay, it's always good to get a feel for what you're working with. Okay, and we know that this c value in standard form, our constant, is our y-intercept. Okay, so if we said that this was 3, let's do 1, 2, 3. We know that's a 3. We know that our graph is starting right here. Okay, we have a negative value out front, so we know we're going to have a downward facing graph. Okay, is it going to look like this? Well, if this was the vertex, then this means at 0 time, the ball was already up here and the ball just started going down. Does that make sense when you kick a football? That you kick it and it just immediately goes down? No, that doesn't make sense. So let's scratch that graph. Okay, we know that it's kicked straight up. Okay, so we know that this football is going up a little bit and then it's coming down. So that kind of looks like how a football gets kicked up in the air. So if we got this piece right here, we can kind of just continue the rest of our graph right here. So now we have a rough sketch. We have our y-intercept. We know that we're going to have some vertex right here. We know that we're going to have an intercept right here and an intercept right here. Okay, but here's the big kicker. Ha, you like how I did that? Football's kick. Here's the big kicker. How long will it take to hit the ground? So it didn't say how long will it take till it's 10 feet. How long will it take till it's 3 feet? If we're asking for it to hit the ground, how many feet would that be? This is something that you got to kind of ask yourself and figure out within the context of the problem. Well, if we're 3 feet above the ground when we kicked it, how many feet would the ground be? You guessed it, 0. So if we're at 0 feet, that means we are looking for, you called it, one of the x-intercepts. Okay, so let's go ahead and look. Can we factor this? Pause the video, try and factor that. Remember, do your a times c value, see if you can do it. Come on. Alright, welcome back. As you can probably tell, since I got the calculator up, that unfortunately, my friends, we cannot factor this. So we are going to turn to our calculator. This probably should have gave it away to the instructions in there saying round to the nearest tenth of a second. Alright, so let's go ahead and enter this in. Boom, negative 16x squared plus 54x plus 3. And then let's just hit graph. Let's see, maybe we can see it. Oh, buddy, that is not good. That looks way off the map. But do we really need to adjust the window? We know that we're going to have a negative answer, which is probably really, really small over here. Don't think we need it. We can't ever deal with negative answers. Let's go ahead and just go straight to the big boy, right? The one that is positive and is going to be our answer, and that is this little sucker right here. Okay, so we know that we're looking for when it hits 0. That means it is an x-intercept. So we're going to hit that calc button. We are going to find one of our zeros. Boom. And then remember, you got to use the left or right arrows. We're tabbing to the right. It's probably going to take a while to get down. As you can see, these values changing. Don't feel like you got lost. Okay. You got to play around. Look at those values. So right now, boom, right here. And then immediately jump. All right. Boom, we got to find it again. Left or right, never up or down. Alright, there we go. So now I am left bound to this point. I can hit enter right here. and I'm going to hit right one more time. Just to be safe, I'm going to do it again. I'm going to hit enter. I found my right bound. This point is in between those two. I'm going to hit that guess. Boom. Now I found my 0. So when y is equal to 0, I got 3.42967. It wants me to round to the nearest tenth of a second, so that's going to be 3.2. So t is going to equal 3.4. 3.4 seconds. Boom, and that's it. That one is so easy when we do it with the calculator, just because remember, we cannot use this solution here. So, alright gang, that is all I have for you guys today. Sorry it took so long, but you know I enjoy talking to you guys. I like rambling on and on. I hope you guys like hearing me. Remember, hit that like button down below. Subscribe. Alright, I will catch you guys on the next one. Peace.